Introduction to Binary Heap. So hello everyone, welcome to today's lecture on the topic of binary heaps. We're going to be exploring the fundamentals of binary heaps, their properties, operations, implementation, and applications. Introduction to heaps. So a heap is a special tree-based data structure that satisfies a property called the heap property. So there are two types of heaps. First one is min heap, and the second one is max heap. In a min heap, the key at the root must be the minimum among all keys present in the heap, while in a max heap, the key at the root must be the maximum. Heaps are widely used in implementing priority queues, which are data structures that support efficient retrieval of the highest or lowest priority element. And they are also used in algorithms like Dijkstra's shortest path algorithm and heap sort. Binary heap. So a binary heap is a complete binary tree that satisfies the heap property. Uh, this means that all levels of the tree are fully filled except possibly for the last level, which is filled from left to right. The binary heap has two main properties. First one is the structure property. Second one is the heap property. So the structure property ensures that the tree is complete, and the heap property ensures that in a min heap, the key at the root is less than or equal to the keys of its children. And in a max heap, the key at the root is greater than or equal to the keys of its children. And here is an example implementation in Python. You can see this is binary heap class, and we have several methods. Types of binary heaps. So we talked about in the previous slides that there are two main types of binary heaps, min heaps and max heaps. So in a min heap, the root of the heap is the minimum element among all the elements present in the heap, and this property is recursively true for all nodes in the binary tree. And in a max heap, the root is the maximum element, and this property is also recursively true for all nodes. So these properties make binary heaps useful for efficiently retrieving the smallest or largest element, respectively. And we can see the example implementation of min heap and max heap that is a subclass of binary heap. Everything is the same except in the heapify up process. We can see that in this while condition, we have inequality switched. So for min heap, we execute code in while loop if self parent index is greater than self heap index. For max heap, we do that if self parent index is less than self heap index. Operations on binary heaps. So let's talk about some basic operations that can be performed on binary heaps. The first operation is insertion. In order to insert a new element, we'll need to uh, add the element at the end of the heap and then compare it with its parents by calling heapify up. If it violates the heap property, we swap it with the parent and repeat this process until the heap property is restored. Operations on binary heaps, deletion. And so the next operation we're going to talk about is deletion. In order to delete the root element, we can replace it with the last element and then compare this new root with its children. As you can see in this delete, if the length is 0, we return none. If length is 1, we return this the element in the heap. Otherwise, we set root to be the first element in the heap, and we pop that heap, and we will call heapify down. And we can see that in heapify down, we are swapping the element with the smaller or larger in max heap child to and repeat this process. Operations on binary heaps, heapify, extract, and peek. So in the heapify operation, we are basically adjusting a binary tree to satisfy the heap property, and heapify can be used to build a heap from an arbitrary array of elements by calling it on all non-leaf nodes starting from the last one. The extract min or the extract max operation removes the root element, which is the minimum in a min heap and the maximum in a max heap, and that restores the heap property. The peek or find min max operation simply returns the root element without removing it from the heap. Binary heap implementation. So binary heaps are typically implemented using arrays, and the root element is at index 0, and for any element at index I, its left child is at index 2i plus 1, and its right child is at index 2i plus 2, and its parents is at index I minus 1, integer division 2. So this array representation is efficient and allows us to easily navigate the heap. For insertion, we add the new element at the end of the array and percolate it up to restore the heap property. For deletion, we replace the root with the last element and percolate it down. In order to build a heap from an arbitrary array, we call heapify starting from the last non-leaf node and moving upward. Binary heaps have several important applications. One of the main uses is in implementing priority queues. which are data structures that support efficient insertion and deletions while maintaining the uh, priority order. Here is an example of a priority queue. If you're using Python, you can just uh, import heap queue library and then just create an empty priority queue and then use uh, the method from heap queue, which is heap push to add element to the priority queue. And then you can use heap pop to extract the smallest element. Another application of binary heaps is Dijkstra's algorithm. Um, what this does is, given graph, uh, this algorithm will find the shortest path. So what it's doing is, in this algorithm, a binary heap is used to efficiently get the vertex with the minimum distance. And lastly, another important application is in heap sort, which is a comparison-based sorting algorithm that uses binary heaps to sort elements efficiently. Conclusion. So in summary, binary heaps are a crucial data structures for implementing efficient priority queues and are used in uh, al many algorithms and applications. Uh, it is important to understand their properties and operations in order to utilize them effectively. Uh, this is it for the lecture. Thank you everyone for listening.